Welcome to Road to OpsCon. My name's Christina Hogan and I'm here to talk to you today about learning to fail better, which are some perhaps radical ideas from the practice of cloud system administration. First, let me introduce myself shortly. I've been working in IT for a while now. In 2001, Tom Limoncelli and I published the first edition of the practice of system and network administration, and since then we published a second edition with Strada Chalop. Just last year we published the practice of cloud system administration, which we also called Volume 2, with the implication that the original book is actually Volume 1. Actually, for the first time here and also at the LISA conference this week in the States, we can announce that we're also working on the third edition of Volume 1, which should come out about a year from now. It has quite a lot of new material. Some of it's already available on Safari rough cuts. If any of you have Safari access through work, you can take a look, and if you give us feedback, it does come straight to us and we have time to incorporate any substantive feedback. The rough cuts area on Safari, it's material that hasn't gone through copy editing yet, so don't worry about all the typos and things. The copy editors will catch that, but if you have something substantive, please feel free to let us know. Volume 1 is focused really on the enterprise, where most services are built using open source packages or commercial off-the-shelf software. Volume 2 is focused on large distributed systems where the developers and operations staff work in the same company, and that leads to two very different operating environments. We've been asked, why did we call the book The Cloud System Administration? It's really a marketing term. We all love the cloud, or at least our CIOs do. And as we know, the cloud solves all problems. So what is it really? Well, actually, it's just distributed computing, which has been around for decades. Distributed computing provides better scaling and better reliability. And the principal tenet of distributed computing is just to divide the work among many different machines. For all but the most simple cases, this requires some software to coordinate the distribution of work and the correlation of the results. Some examples of distributed computing are genomics or computational fluid dynamics, where you have hundreds of machines working on the same problem, or just a normal corporate web server where you have maybe 10 machines each handling a tenth of the load coming in, or Gmail for storage where you have tens of thousands of machines storing the messages from Gmail. Distributed computing can do more work than your single largest computer. You can have more storage, more throughput, more memory, more compute power. And if you try and prove me wrong by building a computer bigger than my data center, I'll just take many of your computers and build a bigger data center. So distributed computing always lets us scale beyond what was previously possible. But scale brings challenges. If you're trying to scale to millions of users, you have bigger risks, your failures are much more visible, and your costs can spiral out of control, both hardware costs and operational costs. To meet those challenges, we need some radical ideas on how we can reduce risk, increase reliability, and come up with efficient solutions to control our costs. We'll need automation, and we need to figure out how to reduce overhead while still providing a reliable service. To do all of that, you first need to make peace with failure. You're building on imperfect parts. Parts are imperfect, networks are imperfect, systems are imperfect, code is imperfect, and people are imperfect. And people are one of the biggest causes of failure in our world. So if you're building on these imperfect blocks, you need to expect failure. So you just need to know how to fail better. You've got to move away from the mentality of trying to avoid failure by building on the best, most reliable hardware that you can find. Even if you buy the best, most reliable hardware, it's still going to fail. And if it doesn't fail, you're going to need to take it down for maintenance. So instead, embrace failure and get good at it. So these are some of our perhaps radical ideas on 3 ways to fail better. The first is build your super reliable service using cheap, unreliable parts. The second is that if a process or procedure is risky, don't try and avoid it, do it a lot. And finally, don't punish people for outages. It's counterproductive, and we'll try and prove to you why. So, starting off with the first of those, using cheaper, less reliable hardware to build your reliable service. When we build a service on reliable components, we're paying extra, like an insurance premium, to guard against failure. However, if you take a step back, you can look at how you can spend your money more wisely. One example is, if you go and rent a car, say if you flew in today and you get to the airport and you look to rent a car, well, the car rental company is going to try and sell you extra insurance, just in case you have an accident or your car is broken into or whatever. And of course that's an extra cost. But if you look at your existing car insurance policy for your own personal car, you may find that it covers many of the things that the car insurance company are trying to offer you. And for some people, their homeowner's insurance policy actually covers theft of their personal property when they're away from home. And depending on the credit card that you have, if you rent your car using that credit card, they may also cover the cost of this additional insurance. So you're just paying for it many times over without getting any additional benefit out of it. It's similar when we build services. The old way of thinking and of writing code was to assume that hardware was perfect. Memory never fails, computers don't fail, the disks never fail, the hardware will just work, which is not true. We're building on imperfect parts. And so in the old way of building services, we would try and simulate the perfect world. We would get a high-end server with RAID disks, dual power supplies. We put in a data center which has a UPS, and we buy the gold maintenance from the vendor so that when something fails, we get our replacement parts really quickly. And then at some point we realized that, well, we're still going to need to take this server down for maintenance, or maybe we can't actually scale to the stage that we want to, so we get a load balancer, and we get more servers, and we put them behind the load balancer. Then we need to bring some code changes in to distribute the work across all of the different machines. And at that point we realize, well, we also have a single point of failure in the load balancer. So we need a second one of those. And again, you're spending money on reliability at every single level. What we say is, don't do that. It's not efficient or cost effective. You should build your reliability into the software. You need to do it anyway in order to distribute the load. When you put it in software, you pay once when you're developing it, and then after that it's free to deploy it as many times as you like. When you buy high-end hardware with reliability features built in, you're paying that extra insurance premium every time you buy the new piece of hardware. So you've got the best hardware, you've got the code to distribute the work, and you're double spending. Instead, just write the code to distribute the work and have code that does not assume that hardware is perfect and never fails. In the end, we run services, not servers. Services are important because people rely on them. Servers should not be important to you. You shouldn't spend a lot of time trying to repair a server, bring it back to life. Think of servers like cattle, not pets. You put redundancy where you need it. So yes, you need 2 load balancers to make sure that a single load balancer failure can't take you out. But then you put lots of efficient servers behind that, and you need to be able to pull one out and put another one in to replace it very quickly. Now, this is one place where it's important to realize that with lots and lots of small servers, your operational costs can get out of control unless you have the automation in place to just be able to put in a blank machine, build the OS, put the applications on it, and get it into service really quickly. If that's a manual task, your operational costs are getting out of control and you're losing the efficiency of getting all of these super efficient servers. So these techniques work for huge grids of machines like Google and Amazon, and for everyday systems like your corporate website as well. But one thing to remember is that big resiliency is cheaper. When you have lots and lots of machines, you have a lower overhead than if you have just a couple of machines. So if we look at buying some high-end servers with lots of CPU power and so on, and then we want to make it reliable, we need 2 servers at least to have a reliable service. And at this point, you shouldn't run those servers beyond 50% capacity, because if the disks catch fire on one of the servers, all of the load has to shift over to the other one, which means that you have to run at 50% overhead. That's a pretty high insurance premium. On the other hand, if you have 10 servers and you want to be able to deal with one failing, you can run them all at 90% capacity, and when one fails, you still have sufficient capacity to run your service. So your overhead is only 10% in this case, rather than 50%. Also, if you have cheaper resilience, so you have low overhead and you have cheaper servers, more resilience is more affordable. So the previous example was what we call N+1 resilience, where you have sufficient capacity to run your service even if one machine fails. N is what you need to run your service, and then the +1 is what you've got for extra. You can have N+2, N+3, and so on. And if it's cheap to increase that N, then you can get more resilience rather than just N+1, which gives you a more reliable service. Also, if you look at doing N+3 resilience in a situation where you have one server that could handle all the load, so one big server, well, now you need 4 big servers, so you've got 4 times the cost. Where if you have an array of servers, in this case I've said 18 servers can handle the full load, you can lose 3, so you've got 21. It's 1.16 times the cost. You could argue to me, well, I've got this big high-end server with lots of resilience built in. I don't need to do N+3. I only need N+1 for my reliable server. Well, we look at that situation too. You're still running at twice the cost with 2 of those servers versus 1.16 times the cost with your array of cheap, unreliable servers. And in the cheap, unreliable, you've got N+3 resilience. But before you get too carried away and say, well, now I have this big budget that I can just keep spending and I can go up to N+10 resilience and it's going to be better, you've got to think the right amount of resilience. What do you need? You need to say, my service is going to be up, say, 99.9% of the time. And I should build, and that's my service level agreement with you, I should build the service to meet that agreement, but not to go beyond it. So this is, when I was talking about controlling costs and efficiency, think about your service. How much do you really need in terms of resilience? Don't just go wild spending money. There's also other ways, if you look at your servers, to keep your costs down. So if you have something living in a data center, it doesn't need a graphics card. And there's other ways. So some companies, for example, Google a while ago took some pretty extreme measures to try and keep their per server costs down. They went to look at RAM. They needed lots and lots of RAM. And they thought, well, what's the cheapest way that we can get this RAM? Our software does not assume that RAM is perfect, that there will never be errors in RAM. Even with the highest error correcting RAM, you're still going to get some errors. So we write software to cope with the errors. At that point, why buy the error correcting RAM? Why even buy error detecting RAM? You just get the normal RAM. But let's go one step further. What is the difference between these different types of memory? Actually, it's just the number of quality checks that they passed when they were being made. So error correcting passed the most quality, error detecting next most, normal was minimal level of quality checks in order to be sold. What about the rest of it that didn't pass these quality checks? Somebody said. So they went and spoke to the RAM manufacturers. And they said, well, that's no good, we just throw it out. I said, well, how much would you charge us to send it to us instead? What can we buy it for? And they said, well, very little, but, here's a cost, pennies on the dollar for this RAM. So all of the RAM that failed quality checks, Google bought for a really cheap price. Then they stuck it in machines, did some minimal amount of checking on it. If it was good enough for them, they put it into production. Some of it wasn't, and they just tossed it out. But it was so cheap that it really didn't matter. And that way, they built their resilience in software because they were doing it anyway. And they had dirt cheap RAM, and they were able to get terabytes and terabytes of RAM for way cheaper than any of their competitors were. So hopefully I've convinced you that the best way to build your reliable service is to use cheaper, less reliable hardware and put your resilience in software. The second thing I said was that if a process or procedure is risky, you shouldn't avoid doing it, you should actually do it a lot. You've got to realize there's a difference here between risky processes and risky behavior. Risky behavior is just risky. Shooting yourself in the foot, nothing's going to make it any less risky. Risky behaviors are just risky. On the other hand, risky processes can be improved through practice. These are things like software upgrades, database failovers, network trunk failures, and hardware hot swaps. Things that people are a little afraid of doing because they haven't done it in a while, and if something goes wrong, there'll be a huge outage, and they don't want to be the one who's shot. We can look at an example for Stack Exchange. They have their main site in New York City and a disaster recovery site in Oregon. They have a lot of applications that are always on, used by people around the globe. There's no particular time when it's good for them to be down, but they needed to move office in New York. So they were going to have to fail over while they were moving office, fail over to Oregon, move all the servers and everything to their new location, build it all up again, and then fail back. the process was risky. They hadn't done it before, they kind of knew how to do it, and my co-author Tom, who's working there at the moment, said, let's not do this for the first time when we're moving. Let's practice ahead of time. So they did a series of drills. The first drill, it took more than 10 hours to do the failover. It needed 3 different teams to be hands-on. They found some people were single points of failure. They wouldn't be able to fail over unless those people were around, which is never a good plan. Because do you fly them back from Caribbean when they're on holidays just because you needed to do a failover? And they found at least 30 things, more than 30 things that needed improvement. So they did a series of drills. That first time they filed more than 30 bugs. It took more than 10 hours. The next time round, it took 5 hours and they filed 20 bugs. Next time, filed 12 bugs and it took 2 hours. And then the last drill, they filed just 5 bugs and it took 1 hour. At that point, they felt, okay, we're ready to do the office move. We can do this failover and fail back pretty smoothly. Why do drills? Well, you don't want to find all of those problems in a crisis situation. You want to find them ahead of time and figure out how you're going to improve. So each drill surfaces various areas of improvement. Also, everybody in the team gains some confidence with the procedure. It doesn't have to be the most senior person, and it shouldn't be the most senior person doing the drill each time. Maybe the first time, but then after that, you can have each member of the team go through it. They will also discover different things that, say, the senior member of the team just knows and takes for granted that actually could be improved, better documentation or whatever. So everybody in the team gets confidence, and we also say small batches are better. So if you're doing something once every 3 years, a lot of other stuff is going to have changed in the meantime. But if you do it every couple of months, or even more frequently, not so much else has changed in the meantime. And we'll look at that a little bit more later. Another example is a company that did a Datacenter Powerdown every 3 months. They had a well-documented, up-to-date process. They knew what the order of shutdown of machines should be, because in the Unix world, sometimes if you shut down one machine ahead of another, that other one hangs, and you have to bring this machine back up in order to shut that machine down. So they had all of these dependencies documented. They knew their run order, and they were pretty quick at it. Well, one day they discovered the air conditioning system was leaking into their raised floor, underneath the floor, and there was water right next to the power sockets. At that point, the management had to decide, do we just go in, hit the big red button, let everything come down, or do we pull out our process and do an orderly shutdown where we've less chance of killing some hardware? How much time do we need? Well, because they did this every 3 months, they could say, this is how long we need to shut down. Management could say, yeah, okay, I think we can manage that. Do your orderly shutdown, and then we hit the big red button. And it went flawlessly. No machines were damaged, and they got the problem fixed. Software upgrades are often a big one. The traditional approach for software upgrades, particularly for off-the-shelf software or packages of open source software, is that you go through months of planning, you find lots of incompatibility issues. It's a very expensive process. When you make a mistake, it's really visible. And by the time you're finished, you've got to start all over again because there's a new version out with features you want or bug fixes you need or whatever. The distributed computing approach, and really this works only in a DevOps environment where you've got the developers on site, is that you have very high frequency upgrades, maybe many times a day or many times a week. You can scale this to enterprise environments where you build up a similar kind of process to what they have in the DevOps environment. It's fully automated, the builds are automated, the testing is automated, and actually the deploy to production is automated. It's easy to fix failures, and it's cheap, which encourages experimentation and innovation. And say that big bang releases once every 3 years or whatever are inherently risky. Small batches are better. There's less changes in each batch, so it's easier to identify the source of a problem. You have less lead time in debugging problems because for the developer, the code is fresh in their memory. When you find an issue, they can understand what they were thinking at the time and resolve it much more quickly. Also, the environment has changed less. There are less external changes to break on. There aren't other packages that have been upgraded in the meantime. Maybe the OS has changed in the meantime, whatever. The environment stays pretty continuously the same if you're doing frequent upgrades, and so you have less things that you'll break on. And actually, everybody is happier. I don't think anybody likes the stress of a once every 3 years upgrade that they really don't know what's going to happen. And in a DevOps environment, the developers see their code getting out to the end users a lot more quickly. I would say risk is inversely proportional to how recently you have done it. Another example at many places is backups. You may do backups, but how often do you restore your backups? If you've never restored the backups, then that's going to be a very risky process. You're not entirely sure what's going to happen. Another example from Google, their backups team actually has a bi-directional SLA. So sure, we'll do your backups as often as you want, but unless you do a restore onto your live production service at least once every 3 months, we will stop backing it up because you don't know that your backups work. And a backup is only as good as the last time that you knew you could restore it. A very unrisky process is if you've got a load balancer with lots of web servers behind and they're unreliable and they fail all the time and the load balancer is constantly switching between them, you know it works, you're completely comfortable with it, and depending on the amount of resilience you've got, you may even say, yeah, don't page me at night for that, I'll fix it in the morning, it's fine. Taken to other extremes, Netflix has something that they call Chaos Monkey, which it's a process that goes and randomly reboots machines. It just picks something and reboots it at random. It's not scheduled, you get no warning. It just goes and shuts something down to make sure that the failover process works. The idea is to keep Netflix on its toes. You never know when your machines are going to fail. And in fact, they built up what they call the Simian army. They also have Chaos Kong, which every so often takes an entire data center down, just to make sure that everything works even if a data center goes offline. And if you've got something like that going on in the background, you're going to be really sure that your processes are automated and you don't need to do anything, that everything just happens automatically. The other member of the Simian army is Latency Monkey, which introduces random latency on particular links so that their processes automatically detect the latency and route around it. So that was The second one, if a process or procedure is risky, do it a lot, maybe even do it automatically. And then the final part is don't punish people for outages. I don't know how many people here have been in a company where an outage happened and the next thing that happened was everybody was looking for the person to blame and fire. I've been there. And it's not a happy place to work. There will always be outages. You need to make peace with failure. Everything you're working with is imperfect, so things will fail. And getting angry about it and looking for somebody to blame and fire is equivalent to expecting them to never happen, which is irrational. So the outdated attitudes about outages, which unfortunately still exist at many companies today, are to expect perfection, 100% uptime, and you punish any exceptions to prove that you're serious. You fire someone. The results are that people hide problems. They don't want to be the one to be blamed and fired. They stop communicating. There's no transparency in the company, and small problems get ignored and turn into big problems. The right way to think about outages is to set some uptime goals. Say 99.9% uptime, give or take 0.05%. 99.9% uptime means that you've got 8 3/4 hours a year of downtime. That gives you an error budget. You can take your error budget and split it into quarters and into months. And when the error budget is exhausted, you say, okay, stability is number one priority. No new releases, no configuration changes, just leave the service alone until the error budget is replenished next month or next quarter. On the other hand, while you still have budget available, you can push as many releases as you like into production. You can do as many configuration changes as you like. You've still got a budget surplus. And to keep the budget surplus, you need to invest in automation for testing, smooth rollouts of new releases, and smooth rollouts of new configuration settings, and also roll back. So if something does go wrong, you can fix it really quickly and keep your error budget in surplus. You need to anticipate outages and keep in practice by doing drills so that you can improve your processes and always keep your error budget in surplus and stay within your SLA. Most places, 3 nines, 99.9% is perfectly adequate. You don't actually need anything more than that. If you go up another 9, 4 nines, that's 52.5 minutes a year of downtime, which is not a whole lot. The other thing to realize is that there is no root cause. You hear root cause analysis. There is no one root cause. There are contributing factors. None of these factors on its own would be enough to bring the service down, but together they cause the service to go down. So when you're doing a root cause analysis, look for the root causes, not just one, all the contributing factors. After an outage, write a blameless postmortem document. You're not looking for whose fault this is. You're looking to find all of those contributing factors. Identify what happened, how it happened, and how you can prevent that from happening in the future. The people who are writing the document and the other teams involved should take responsibility for finding ways to implement long-term fixes, for finding some short-term fixes, and for educating other people on what happened. Each team should look at their own component and say, how could I do this better? If I had done something a little differently, could that have prevented this outage from happening? It doesn't mean it's my fault, it just means that I could do something better and make things better for the company overall. Here's an example of a postmortem document. It's a little summary up the top, what happened, how long did it last, and what were the causes behind it. In this case, there is just one root cause, but and what are your recommendations? A bit of background information, the schedule of the events, and then what went right. So in this case, to say the use of Puppet meant that we were able to revert the bad changes quickly, and everybody worked together to fix the problem. What needs improvement? Well, the firewall rules were hard to understand and update, and we could make that better, and we need better testing on the firewall rules. What can we do immediately? Improve the comments. There were incorrect and misleading comments. And long term, we have some other projects in progress that we need to do. The feedback from that post-mortem report, which was published widely, both within the company and externally, so customers could see it, and this is feedback from a customer, it was, I don't know about anybody else, but it's nice to know what happened, how you handled it, how you plan to prevent this from happening in the future. Really great. Thanks for the good work. So, that was the end of the third part. Don't punish people for outages. Some of the things that I would like you to take home from this is, first of all, cloud computing isn't anything magical. It's just distributed computing with a marketing term. You should use cheaper, less reliable hardware to build reliable services and build your resiliency through software, and pay for only the reliability you need. Also, if a process or procedure is risky, don't be scared of it, do it often, get comfortable with it, and know that you can do it well. Practice makes perfect. Also, don't punish people for outages. When you do that, you can't get that same level of transparency as to what happened, and people are afraid to offer solutions and improvements in their own area because they think the blame may shift over to them. You get a much better result if everybody knows that you're not looking for someone to blame or fire. I will say that in an era of outsourcing, this does become a bit of a challenge because the company that is purchasing the outsourcing service may be looking to blame the outsourcer in order to levy charges against them. And the outsourcer is going to be afraid of getting blamed and being billed for having caused the outage. So even in an outsourcing environment, you've got to have this culture where you're not looking to lay the blame and charge somebody money for it, or your service overall is going to suffer. So, are any of these ideas really radical? I'd say actually not so radical. If you look at your home life, we build houses by putting resilience where we need it, on the outside. We have big strong front doors with locks on them, we have alarms on our windows and doors, but internally we can move around freely. We don't pay extra for those things inside. Risky processes, do them often. Practice makes perfect. You don't expect to be able to get on a bike and cycle it the first time out. You look at ways that you can improve your balance, get comfortable with pedaling, and eventually you'll get there. Equally, if the only big meal that you cook every year is Christmas dinner, It's risky. It could go wrong. So invite people over to dinner more often. Have big dinner parties. Practice makes perfect. And then Christmas will be less stressful and more enjoyable for everyone. And also, don't punish people for outages. Where does the blame lie? Just look for better ways to do things in the future. Deal with the small issues as they arise and look at how to improve the process going forward. Having small, difficult conversations frequently help us stay in practice and develop better tools for when we need to have the big, difficult conversations. Deal with problems when they're small. Don't expect loved ones to be perfect. It's irrational. And that's why good relationships include healthy portions of forgiveness at work as well as at home. So those were some of our radical ideas on how to fail better from the practice of cloud system administration. And hopefully after today you'll say, actually, they're very reasonable ideas on how to fail better. And I hope you'll adopt them in your organization today. If you like this talk, there's more like it in the book, and there's a discount code for people at the conference today. And now we have some time for questions and answers. Anybody got some questions? Not, maybe we take a break.
Probably more around than a question.
Okay.
You say that. Oh. Thanks. You say the good part, how things work, how should work. But for instance, I switched from Solaris at Sun Def to Ubuntu, and they choose to automatize with Ansible. Good, it does work, and DevOps solutions are good. However, it's a total fail for bare metal deploy. We miss many technology for that. For booting a system, we have Cobbler. We have to set up the FTP, API proxy, and many other stuff. So it's not simple. It's not easy to automatize. Proceed is a nightmare. Also, Kickstart from Red Hat, it's less a nightmare, but it's still a nightmare. We need many more technology in this sense. We still haven't. That's it. Thanks.
Yeah,
sorry for
sure.
my English.
It's fine. It's better than my Italian. Absolutely, you need more processes, you need more automation, and I'd say actually the first book, volume 1, has some suggestions there of just start with documenting what you need to do and getting other people to use that documentation, because they'll spot places where you've made assumptions or you just know, oh, that's not quite right. And so you start with good documentation, then you look for little bits of it that you can automate. Don't try and automate start to end in one go. Automate the bits that you can that are easy, and that will improve things already. And then over time, eventually, the whole thing or the majority of it gets automated, or the common case is automated, and there's a few exceptions that are not. But yeah, it takes time. Anyone else? Okay, thank you all.
Beh, ci siamo, grazie.